So what we were doing essentially in the last lecture, that is lecture 7, most probably, yeah, so lecture 7. So at the start we discussed a few of the missing links for the previous, let us say lecture 5 and 6. We were discussing those, and after that we started the topic of quantization. Okay. Now this is very much important to study, reason being that we are still not done with the start of digital communication. It means if you have an analog waveform, we have not yet completed its conversion to the digital format. Digital format means the things have to be discrete, and in most of the cases, those discrete things we should be able to represent them by some finite levels. Okay. So we have not yet finished that. So we have now come to the point where we have converted our analog waveform to a set of discrete values, and now those discrete values we want to enforce that they belong to a finite set. It means that every discrete value should take one of the values from a set. So this process is primarily done through quantization. Okay, you are quantizing that if at all I accept this means, or you can just go and see the dictionary meaning of quantization or quantize, you will find out that there is a full relationship with what we are doing. So we said that the process of transforming the sample amplitude MNTS of a message signal MT at t equal to NTS into a discrete amplitude VNTS taken from a finite set of possible amplitudes. This is what I have already said, that we have MNTS, that is the discrete values or the sampled values of the analog waveform, and now we want to enforce that each M of NTS should take some value VNTS which belongs to a finite set of possible amplitudes. Okay. Now this is a very important step because now we are coming very close to the start of digital communication. Okay. So this I gave an example. Let us say that there is a device which takes the minimum amplitude as minus of MP and then the maximum is MP. That is the range of amplitudes which it can absorb, which it can process. And let us say you set a discrete value inside, or you send a discrete value inside, so it will check that, let us say it lies in which of the interval. These intervals are denoted by these dotted lines. Okay. These dotted lines. Suppose your sample lies in this interval. So this value now will be replaced with the midpoint of this interval. Okay. So this is what is done in quantization. And if at all we have a uniform spacing between the intervals, then you will find that the gap between the 2 points will be 2 MP by L. That is what we discussed last time, that you take the full amplitude as a range. Range is MP minus minus of MP. So it is twice of MP. So twice of MP divided by the number of levels you are dividing. Okay. So it is twice of MP by L. Now, we started with the concept that we, instead of choosing the lower point as the accepted value, we will choose the midpoint as the accepted value. Okay? So we will be right now focused on choosing the midpoint only. There is always a possibility. So you can say that why, if at all something lies in this, I can say that if it is greater than the midpoint, it should take a value mk plus 1. If it is less than the midpoint, it should take the value mk. All these designs, I would say, are possible. They have been well studied, and in application dependent I think scenarios they have been used as well. But for the purpose of study right now, let us choose one concept. Okay, so we will choose that concept which is popular in textbooks. Now, why are we doing that? Because textbooks have been written by people who have I think seen this area grow for at least 20-30 years, and they have referred to a lot of papers. So maybe that this strategy works fine in most of the cases. That we will choose, let us say if your sample lies anywhere between mk and mk plus 1, so you will choose the midpoint, v of k. So v of k is now the sample value which entered into the system. Suppose something which entered in the system lies here. Okay, so you will say now that this is not the value is now vk. Okay, this is some sort of a mapping. Okay, and what I feel is that this cannot be recovered. See, if you are given vk, you cannot tell which value. So there is definitely an error which we are putting in the system deliberately, and this error cannot be completely removed. Although this magnitude of error can be decreased by increasing the number of levels. Okay, I hope that this is clear to all of you, that what I mean, that this is a sort of a mapping, or this is a sort of an operation which the problem which it will give is that if at all I know vk, so can I say that what the sample value is? No, I cannot, because the sample value can be anywhere between mk and mk plus 1. So this is a deliberate, what we call as introduction of error in the system, but we will see that this error in a lot of systems, let us say in telephones, in voice communications, it doesn't affect the quality of reception. Okay, you will be able to clearly identify the speaker and understand what he or she is speaking. Okay, so but if at all we have introduced some error, so the benefit is observed in the communication scheme. It means the digital communication we have discussed is more robust than analog communication, and secondly, it can have repeater stations easily put up. So your telephone lines which were there in earlier days, they used to work on wires. Okay, so let us say if your wire runs from your home to the telephone exchange, and from telephone exchange to the central exchange and to several other places. So the losses which were incurred in the transmission are now, if at all it was analog communication, so it was difficult to recover the voice properly. But with digital communication, we can put up repeater stations. Let us say some repeater will be put nearby to your home, which will take the signal transmitted by you. It will freshly generate the pulses and transmit. Okay, so this is one of the benefits of digital communication, because of which we accept this introduction of error. Okay, so this is what the motivation is. We said that, let us say that there are L levels. We have already said that there are L levels. So this K will belong to 1, 2, 3, 4 up to N. And I gave a few definitions that I think representation levels is VK, the midpoint are called as representation levels. Then MK, MK plus 1, they are called as decision thresholds. Why? Because you check if it is greater than MK and if it is less than MK plus 1, then the sample will take a value V of K. Okay, so these are called as the decision thresholds. And the spacing between two adjacent representation levels, it means let us say Vk and Vk plus 1 or Vk minus 1 and Vk. This gap is called as a quantum or step size. It is sometimes called as a quantile as well. I mentioned it in the last lecture. You can just, it depends on the textbook which you are reading. But anyways, you need to know that this is the spacing between two representation levels. Okay. Then we came to the concept of quantizer characteristic. Quantizer characteristic means that, let us say, if you plot on the x-axis the possible amplitudes or the possible inputs which this quantizer takes, and on the y-axis you plot the possible values of the output it will give. You will find that this is a staircase function. Okay. Why staircase? Because you observe that mk, any value between mk and mk plus 1 will take a value v of k. So obviously, if I put any input from mk to mk plus 1, I will definitely get all vk. So this will be a straight line. Similarly, there will be a discontinuity at this point, and immediately any value which just jumps off mk plus 1 will take a value vk plus 1. Okay, so this is a staircase function. Then I introduced the point that quantizers are of two types, that is uniform and non-uniform. Okay, so I think at that point we left. So today we'll start from the same place. Okay, so I was just before the start of the lecture, in order to reduce, we can say, the wastage of time in drawing, I just had drawn something. So this is this was remaining that there was one more definition. This is called as partition cell. Okay, so mk and mk plus 1 will be called as a partition cell. Okay, this is a cell. Why? Because the whole amplitude range are now divided into cells. Okay, so this is called as a partition cell, which we denote by J of k. And we know that k will lie from 1 to L because we have divided the whole amplitude range into capital L levels. Okay. So we said that quantization is uniform and non-uniform. Now, what is the meaning of uniform quantizer? Uniform quantizer simply means that the representation levels are uniformly spaced. It means that, let us say, Vk and Vk plus 1. Let me write it down. So it means that this interval, let us say Vk minus 1 to Vk and Vk to Vk plus 1. So the length of these intervals will be same. Okay. So you can say that this. So length of both of these intervals will be same, and this applies for all k. It means if you can put k any value, so for that you will find that all is same. So this ensures that you have uniformly divided the amplitude range. Second case is non-uniform. Non-uniform simply means that now we are not saying that Vk minus 1 and Vk should have the same gap between them as Vk and Vk plus 1. Now, at the moment, this seems quite disturbing. That why this is the case? Why should we design a non-uniform thing? So we will see this. That why do we do that? And basically, in reality, let us say for telephone communications, the landline communications. Right now, if I don't know that because our landlines have now being obsolete, we are now having our routers through which our landlines come. We don't have a dedicated landline from, generally in most of the homes we don't have dedicated landlines from MTNL or BSNL or whoever is the telecom operator, the government operator. We generally have now ADSL coaxial, the ADSL wires coming to our home. They enter into the, basically they then divide the voice and data traffic. So, but if at all voice traffic is still being transmitted over the wires, then this non-uniform quantization is used. Okay, so this non-uniform quantization is being used for wireline communication from the past 50 to 60 years at least. Okay, so you must observe that there is a need to study it because this is in the use. So there must be a reason why this was put up in place. So we will see this. Then there are two types of this quantizer characteristic can be of two types. I have drawn it. This quantizer characteristic can be of two types. It's mid-rise and mid-tread. Okay. Mid-rise and mid-tread. Okay. Now, what is the meaning of it? In general, you will find that the quantizer characteristic is a staircase function, that it has to be. Okay. Because it has to map an interval to a level. So it has to be a staircase function. Now, let us say this is of the type mid-tread. It means that the origin lies at the center of a step. So this is a step, let us say this is a staircase. Suppose PCD. So if at all you are sitting at this point or you are touching this point, it means that the origin, let us say, lies at the center of a step. So this is called as a mid-tread and this is called as mid-rise. Means the origin lies at the center of the rise. So this is origin, this is 0. Okay. So this is this terminology you will find at some places. So it is required to introduce it here. At least Simon Haken does it. Others I have not found. Others I have not found doing it. Let us say BP Lati and Couch. I have not find that much of description about both of them. But since Simon Haken does it, it means that it basically arises at some place. So he has just put up in his book. So let me write it down. So this is that the origin lies in the middle of the thread of the staircase diagram. Thread of the staircase. Okay, and in this case, origin lies in the middle of the rising part. Lies in middle of the rising part. So this is quite clear from the graph, you can see. So let me just annotate it properly. This is input level and this is output level. Okay. And the same follows for the second graph as well. So you will see here that if there is an input which lies between minus 0.5 to 0.5, so you will put the level as 0. Okay, you will assign 0. If it lies from 0.5 to 1.5, you will put a level 1. Okay. If it lies from 1.5 to 2.5, you will put a level as 2. So you can see that we are, let us say 0. So 0 lies in the midpoint. So V of k is like this. Here, if at all it lies from 0 to 1, so it will be put as 0.5. If it lies from 1 to 2, any input value, that is the input level, if it lies between 1 to 2, so you will put as 1.5. So that is the two types of this. Important to note that both the types are symmetric about the origin. Symmetric about the origin. So now with the introduction to the quantization done, let us now study the error which this operation of ours put in the system. Okay. this is intriguing at the moment that we want to reduce the noise in the system, but now we are deliberately putting the noise in the system. So you must be knowing that there must be very strong reasons for doing that. So first of all, let us do the analysis of the error. What sort of error this operation of ours introduces? Okay. So let us say the quantized pulses, the quantized samples are coded. Let us say I have not introduced coding right now. Coding means that simply a binary code or a ternary code is put up. We will see once we are done with the calculation of error and with the mu law and A law, then we will study what this code is. For the time being, just assume that there is some sort of a binary code or a ternary code which represents each of the representation. So okay, let us say V of k is a level. So if we have, let us say, L as 64, so you require 8 bits to represent V of k. Now let us move ahead. Are coded and transmitted as binary pulses. Okay, binary pulses. At the receiver, some pulses may be not meaning binary pulses. It means 0 1 0 1. So either 0 is there. For 0, let us say you put one level of the pulse. For 1, you put another level of the pulse, or some sort of an operation you to do with the pulse. Okay, that's why it's called a binary pulse. Or binary pulse simply means that there are two possibilities of the pulse. Okay, for 0 there should be one thing. For 1 there should be another thing. Okay, so at the receiver, some pulses may be detected. Some pulses may be detected incorrectly. Okay, they may be detected incorrectly. So there are two sources of error. Right now, there are two sources of error. One is the quantization error, that is the operation which we have done, the error it puts in. Quantization error. And second is the pulse detection error. Pulse detection. In most cases, pulse detection error, let us say this is PDE. So PDE is quite small compared to quantization error. Okay. Why? Because we will assume that the power level of the pulses which we are using is sufficient enough to bypass the inherent noise in the system. Inherent noise means that, let us say, something is propagating through the copper wire, so there will be some sort of an addition of the noise. This I think we are not covering in this course, but this transmission of RF signal or any sort of a signal over, let us say, some material will put up some noise. Let us say whatever you are transmitting, you won't receive it exactly. There will be some amplitude distortion, there will be some phase distortion. So these things are generally taught in another course, or maybe if it is part of this course, then we need a separate module for it. But for the time being, you assume that there will be definitely some sort of a distortion put up in the signal which you are transmitting over the wire for the time. Okay. So we'll assume that the power level of our pulse is such that it can easily overpower that noise, or easily it can have most probably an error-free type of a communication, even when the distortions like amplitude and phase are present. So we will see that quantization error dominates our performance. Okay? Dominates means that if at all your quantization error is high, then you have a bad reception, and if it is good, then you have a good reception. So it dominates. So let us study it. Okay, so let us study quantization error first. So let us study this. So let us say that your M of t. So this analysis is somewhat important. You can just sit and follow it. This all follows from the sampling theorem. So we know that we can write k of pi. See, for the time being, this derivation is being taken from Lati. So Lati uses the definition of sinc function as sine of pi x upon pi x. Okay. So the definition which is using, sorry, sine x upon x. So you have to put up a pi here. So at few places you won't find pi, and a few places, other places you will find pi. So this just because the definition of the sinc function. So you can simply write sinc of x as sine of pi x upon pi x, okay, or you can simply define, I think, sinc of pi x as sine of pi x upon x. So these are the two ways. So right now we are using this definition, sinc of pi x. So either way. So I have written it. It has to be at the discretion of the cautious reader to find out that in our notes what are we really using. Anyways, I am giving references as well so that you can obtain the derivations, analogous derivations from there. Okay. So mkts sine sinc of 2 pi dt minus k pi. Let us say this is the samples of this m of t. So we know that in a distortionless manner, in an error-free manner, I can recover m of t by this ideal interpolation formula. This we have derived in our, I think, lecture 2 or 3. Now let us say quantize these samples. That is what I am doing. That I have a set of discrete samples of the analog waveform and I am quantizing them. So let us say I quantize these samples. I quantize these discrete values. Okay. By the quantizer characteristic as described above, and I again reconstruct the signal from those quantities. So I am noting it by n cap t. So let us see कि कितना error आएगा. So let us say I represent the quantized samples as n cap kts, and then I use the ideal interpolation formula again to recover my original signal. So this is the reconstructed signal. Now let us see the distortion component, the distortion or the error distortion component which this operation of ours put in the system. Let us say this is q of t, which is equal to summation over k m cap kts minus m kts. Okay. There is sinc of 2 pi dt minus k pi. Okay, so that is what we have done. We have simply subtracted both of them. We want to know that how much mt is away from m cap t. That is called as the distortion component. And this we write it like in a short form, in a short notation. We write it like this: q of kt is sinc of. So basically now we have constructed the error signal. Now this is the error or the distortion. So q of t is nothing but this. So this is called as the undesired signal. Undesired signal called as quantization noise. Okay, called as quantization noise. So this is the quantization noise which is now being induced by us in the system. So we need to study that how much noise are we going to induce. This the quantification, or you can say the measure of that noise is required for us to know. So for that, let us now see. So let us obtain its power. Okay, so this will tell us that what is the power of the quantization noise, or the mean square, value of Q. Okay, let us now try out. But this will be a small derivation, very easy to follow, and you will enjoy this basically. That it's not that every derivation or every mathematics which is put up in engineering is difficult to understand and follow. A lot of mathematics is logical as well. Means that if at all engineer doesn't know mathematics by any chance, then what will his intuition or her intuition say कि कैसे आप analyze करेंगे? So आप यही करेंगे जो हम कर रहे हैं. हमने कहा कि लेटेस्ट से हम पहले सिग्नल को, ओरिजिनल सिग्नल का फॉर्मूला ये है, रिकंस्ट्रक्टेड का ये होगा, तो दोनों को माइनस करके देखेंगे, इफ एट ऑल वी माइनस इट आउट देन वी विल सी कि इसका मेजर क्या है। मेजर का इंजीनियर्स के पास एक ही तरीका है, वो जानते हैं कि पावर है सिग्नल में, या तो मीन वैल्यू है सिग्नल में, जैसे डीसी वैल्यू है, तो इस तरीके से कोई ना कोई मीट्रिक है उनके पास। तो लेट अस से वी यूज पावर एज अ मीट्रिक, व्हाई? बिकॉज वी कैन एट द एंड डिफाइन द एसएनआर or SQNR, it is a signal to quantization noise ratio we can define, and in terms of that parameter we can design our systems. Okay, so let us move ahead and obtain it. So for the purpose, this is the notation which defines the mean square value. Okay, so this defines the MSV. I should write here. So this is your MSV. This is the notation for MSV. Okay, so this is given by, I think this you have to follow from signals and system, that if at all you know that if the signal is whether periodic or non-periodic, this is the standard formula to obtain its mean square value or the power. Okay, so you integrate it out from minus t by 2 to t by 2 with t in the denominator, and you put limit as t tends to infinity q square of t dt. See, ideally it should have an absolute operator here, which we are told when we study signals and systems, but here everything is right now real. Okay, so we have not said that whether m of kts or m of t is a complex waveform. We have said that it is a real waveform. So we have just not put the absolute operator here. Okay, so now you just put up the expression for qt. So you will get 1 upon t minus t by 2 to t by 2. I think because of my screen sometimes minus t. Okay, so you have summation k q kts sinc of 2 pi bt minus k pi. Okay, and this is whole has to be squared t of t. Now our orthogonality of sinc functions, which we studied in the sampling theorem, the cardinal series, will come into play. So I am simply writing it, I am stating it because we have derived it earlier. So using integration minus infinity to infinity sinc of 2 pi bt minus k pi. Like this, m pi into sinc of 2 pi bt minus n pi d of t is equal to 0 and 1 upon 2b for m not equal to n, then m equal to n. Okay, so this is what we know, that the sinc functions are basically orthogonal in this form. If at all you are shifting them by integer, this sinc of 2 pi bt, put 2 pi bt, I am shifting by integer multiples of pi. So m and n are two integer values. So using this, you can get that q square, the MSV, is given by simply limit t tending to infinity integral minus t by 2 to t by 2 summation over k q square. Now k of t is sinc square 2 pi bt minus k pi. Okay, dt. Remember that this k and this k are same basically. Why? Because of this property. So if at all you are squaring a series, so you will get a lot of cross terms, and all those cross terms go to 0 because of this phenomenon, okay, or this orthogonal property of the sinc function. So you are left with only the square of the individual terms. Okay, so now finally remember that this is an integral with respect to time. So here in this is not a function of time, so only this is a function of time. So we using or shifting the summation and integration or interchanging them, you will get that this is equal to limit t tending to infinity 1 upon T summation over K Q square KTS integration minus T by 2 to T by 2 sink square 2 pi bt minus K pi dt. Okay. So finally we will get limit T tending to infinity 1 upon T summation KTS, okay, by 2 to summation. So this T is going from these tending to infinity, and this is a summation of all the Q terms. Okay, let us say the error terms, the individual errors in the samples. Let us say you take the sample minus the quantized, and you are summing it over in infinite possible values divided by something which is also taking infinite. So what? How do you evaluate that? See here we have used this 1 by 2. If at all you put m as n, so it becomes sine of square, sin square 2 pi bt minus m pi. So let us say m and n or k are quite a general, you can say integer. So for any integer value this holds. So for k this holds. So this is a square. So this becomes 1 upon 2b. So 1 upon 2b comes outside. This remains, and this is what we are left with. Okay. So let us find it out. How can we do that? Okay, right now, though, it seems impossible to evaluate this because we have a summation of infinite terms in the numerator, and in the denominator also we have something which will become infinity or will tend to infinity because of this limit. How do you do that? So we will use the probability argument here, saying that this should be the mean square value of, or the variance you can say, or the second moment you can say of a random variable or a uniform distributed random variable. Let us see how do we do that. Okay. So quantum levels are separated by delta V is equal to twice of MP by L. So right now we are studying uniform quantization only. Since a sample value is approximated, so this is important to note whatever I am writing down, because this will give us the missing link of the derivation. Okay, so after this what shall we do? So we will be motivated by what I am writing down. Since the sample value is approximated by the midpoint of the subinterval of height delta V in which the sample falls, the max quantization error, the maximum quantization error lies in the range minus of delta V by 2 to delta of V, where delta V is twice of MP by. Okay. So this you can observe. See why? Let us see. Suppose we talk of, let us say this is M of k, this is M of k plus 1, and suppose this is V of k. And this is what? This is delta V, the length. I should draw it in the form. So this is delta V. So let us say there is a point, there is a sample which lies here. So you approximate it by V of k. Okay. So what is the error? This is the error. Suppose this is the point. So this is the error which you put in the system. This is the point which is the error you put in the system. Now the maximum error cases are, suppose something is mk plus 1. Okay? Or suppose something is m of k. Now if you are putting, let us say if it is m of k, you are putting the value as v of k. So this is the error which you are putting. So this is what? This is delta v by 2. Okay. So that is what we are saying, that error, if at all there is in the sample, it can lie in this interval, minus delta v by 2 to delta v by 2. The maximum possible error is delta v by 2 and minus delta v by 2. Let us say for those sample values which lie exactly on the boundary of the decision threshold. Let us say if something lies on m of k, then you are approximating it by delta of this v of k. So the error you put in is maximum delta v by 2. But for other samples, the error will always be less than delta v by 2. So it is some sort of a value which lies from minus delta v by 2 to delta v by 2. Okay. Second, fun thing is this. Second thing to know. Sampling rate is 2b. So we have put the sampling rate as sampling rate is 2b. Okay. Why? Because of the sampling theory. So the total sampling rate is 2b. The total number of samples, total number of samples over the averaging interval, t is 2 beta. Okay. Let us say we are studying an interval of length capital T. That is what we have said, that we are studying this whole system over interval of length T. We are we were finally tending that T to infinity, but for the time being, let us say for a particular instance, we are saying that we are studying this for an interval of length T. So because the sampling is 2b, so number of samples which we get in this interval is 2bt. So hence, what does this does? Let us say this is equation number 1. So hence 1 represents the average. Represents the average. Means the average or the mean of the square of the square of the quantization error. Quantization error. Then, so assuming, I think this should be clear what I'm essentially doing. We are saying that the total number of values which we have over the interval of length capital T is 2bt. So we are just taking the error in each of the 2bt samples. We are squaring that error, adding all of it and dividing it by 2bt. So this is the standard formula to obtain an average. Okay, so that is what I have. This follows because of sampling rate of 2b, and this follows from the design. So this is this mk plus 1, and the error line between minus delta v by 2 to delta v by 2 follows from the error base, or follows from our design. Okay. Yes. So assuming that the error is now this assumption I will defend via some argument. Okay. The error is equally likely to lie anywhere in the range we can can obtain as follows. So what happens is that we assume that since we are taking a lot of samples and we know that the error can lie from minus delta v by 2 to v by 2, we can model it as a random variable of uniform nature. Okay. So Q as a uniform random variable in minus delta v by 2 to delta v by 2. So the PDF is P of Q. You know that it has to be 1 upon the length of the, if at all I am saying that it is a uniform random variable. So P of Q is nothing but 1 upon for V line between, or for Q belonging to minus delta V by 2 to delta V. Okay. So we can say that the mean, now if at all this is a random variable, so the mean square value is simply, I think you know that this is given by Q square P of Q dq integrating over the range, that is delta V by 2 to delta V by 2. This is the standard value for obtaining the mean square value. So this, if at all, is given by 1 upon delta V, that is put P of Q. P of Q is 1 upon delta V, integral minus delta V by 2 to V by 2, Q square d. Now this is simple, Q cube by 3, and when you put the lower and the upper limit, so you will get the result as, for you, Q cube by 3, and you let us say substitute the limits. So this is, I think, you obtain as delta V square by 12. Okay, directly putting the result. So there is a difference between delta of V square and delta V ka whole square. Okay, so there you have to be cautious. Delta V square and delta V of whole square are different things. Delta V square can simply mean that V1 square minus V2 square. Okay, this delta of V square can imply. But the delta V whole square means V1 minus V2 square. So that's why I am putting these curly braces. Now substitute delta V in terms of twice of MP by L. So you will get this is 4 times MP square by 12 L square. Okay. And this is nothing but ultimately MP square by 3 L square. This is the formula which you will find at a lot of places for the mean square quantization. That is, say, this is this value. So limit t tends to infinity 1 upon 2 Vt summation k q square kts can be very closely given by this value. Now this assumption of having q, the error, as a uniform random variable needs to have some conditions. Condition means that in what cases we can say. So for it, we need to have a thing like that the analog input takes on all values, let us say in the range minus MP to MP with equal probability. Okay. Equal probability. And another way to say this is that in ordinary PCM applications, see this assumption of a uniform random variable is, I think, inspired or is motivated by some applications as well. So in ordinary PCM, it means that, let us say that PCM was designed for telephone communication, so that is an ordinary PCM application. The number of levels, L, let us say the number of levels, L, is usually high, okay? Is usually high. And the range of variation, variation of the input signal, amplitude variations, amplitude variations is small. Okay, is small. This means length of each quantization. This is important to write. That's why I am writing it. So length of each quantization region, is small because of a very high L. Hence our uniform. Error assumption. May. Okay. Now, what we are saying is that the input which we are taking doesn't have very large abrupt transition. It means that the amplitude is varying somewhat slowly. So, if it is varying somewhat slowly, so it can take all values with equal probability, suppose, within the point of consideration. Okay. Let us say between minus MP to MP, or you can say even if it doesn't take all the values from minus MP to MP, it is a low level signal which slowly varies. So it is observed that over a very large interval, this assumptions of ours, uniform assumption, will hold. Okay. So these are the two reasons which I could find that this also, I felt that they are okay to accept, but if at all they are not at all okay to accept, you can still see that we cannot have a move after this expression. See, what will you do? You do not know, this is a very generalized sort of a derivation. We are not saying what MT is, MKT. I don't know what MKT is. MKT can be, or MT can be a very, any sort of a signal. It can be a sine waveform, it can be a very complex time domain waveform, or it can be a speech signal. The speech signal may not have a very structured form. So if at all you don't have this, then QKTS you don't know, you only know the sample values. So you cannot make any progress after this. So maybe people thought that let us derive it in this manner, and they obtained this expression as the mean square value of the quantization noise. And maybe in a lot of experiments or in ordinary PCM applications, this gave a very good approximation to the quantization noise, which was there obtained empirically. It means there too you have the MT, you have the reconstructed signal, you can subtract and find the mean square value over a large time. Let us say maybe a few hours or something you can obtain. So there they might have obtained that this gives a very good approximation. So these are the two things. So this is what, okay, let us now define it fully. There are a few things which are pending to discuss in this. Okay. So let us denote Q square by N of Q. Now this is what? This is the MST mean square value by NQ. I am denoting it since it is power. Now why we are doing this is because we are habitual of knowing N naught. N naught was the variance or the mean square value of the additive white Gaussian noise, which we have studied in Introduction to Communication Systems. Okay. So to have a good parallel, we have just written this N0 as N of Q. It means now there the notation is N0. Here the notation is NQ. Okay. Then we can say that, assuming pulse detection error, we have already said that we have adjusted the power and everything such that the pulse detection error doesn't dominate. The quantization noise only dominates. So assuming pulse detection error at the receiver is negligible, see, quantization error is not put up by the channel. Okay, it is not put up by the wire over which the signal is moving. This pulse detection error or the problem with the level of the pulses or distortion in the pulses is caused by the medium over which the signal is moving. So assuming pulse detection error at the receiver is negligible, so we can say that M cap T, the reconstructed waveform at the receiver output, is M cap T is nothing but M of T with the addition of the quantization noise. Okay, that is clear. See, we are receiving M cap T. If we assume that the pulse detection error is negligible, it means कि ऐसा नहीं है कि चैनल ने इतना ज़्यादा पल्स को चेंज कर दिया या 0 को 1 और 1 को 0 कर दिया। मान लीजिए वो नहीं है, वो आपने किसी तरीके से बाईपास कर लिया है बिकॉज ऑफ योर हाई पावर और पुटिंग सम इक्वलाइजर व्हाटएवर, लेट अस अज्यूम दैट वो हमने बाईपास कर दिया। तो अब क्या बचता है? क्वांटाइजेशन नॉइज बचता है। तो जो रिसीवर को मिलेगा एम कैप टी, वो हम ऐसे मॉडल कर सकते हैं कि एम टी में आपने एक नॉइज सिग्नल ऐड कर दिया और वो नॉइज सिग्नल क्यू ऑफ टी है। क्यू ऑफ टी हमने ऊपर डिफाइन किया है, क्यू ऑफ टी क्या है। ओके, so why we are doing this is we are defining the SQNR now. Okay, so let the power average. See this, why we are power and we are writing average. I will give you a link most probably in the next lecture to study this concept. This is very important because sometimes you will find instantaneous power written, sometimes you will find average power written. So this you must know what it is. The power of the message. The message signal will be denoted. As, so we are using the same way. Then the signal to quantization noise ratio, signal to quantization noise ratio can be defined as simply divide by the quantization noise variance, or this is the power mp square by 3a. Square proper derivatives, p should be in the foot. Mp square, and this is 3l square. Okay, so simply comes on this divided. So this is called as SQNR. In some books you will find that people are using SNR only. So this SNR can also be valid. Why? Because we have said that pulse detection error is already small. So already small, or maybe the better word was negligible. So this is only the noise Q of T. So I can say SNR as well. But if at all you want to remove any sort of confusion from your minds, that because we have maximally studied SNR in the context of AWGM or Gaussian noise being added to the signal which is transmitted. So in order to clear any sort of confusion, we can use SQNR. Okay, but this is not the only way. You can use SNR as well. If at all, then you have to be specific that this SNR, the noise is quantization. Okay, if at all you are using this expression for SQNR. Okay, so at this point we are done with the derivation of this quantization noise. With I think you can say the derivation followed some say a sine wave type of a system, that we were deriving something, then we have to go back and assume that Q is a uniform, that error is a uniform random variable, and then we came up with this expression. See, we had to do it because we were stuck at this point, and because of the general nature of the derivation. We have not said what MT is. Okay, so that is why we have to resort to these techniques, and empirically this would work fine. It means it has been checked through experiments that indeed this expression is quite a good approximation to at least speech signals. Basically, PCM has been mostly used in earlier days in the context of telephone communications. Okay, in 40s and 50s, when this telephone communication was taking birth, So this PCM was then used there. Okay. So typically, let me write it down. So now we are done with this. So typically, the L array number, the L array. Why I am saying L array? Because K takes the value from 1, 2, 3, 4 up to capital L. So the number of possible values of K are L. So that is why it is called an L array. So L array number K, that is the kth representation level. Kth representation level of the quantizer. Is transmitted to the receiver. The receiver in binary form. Okay, that is, I think I said it in the beginning, that we will have a code type of a system where we will assign a binary code to the number K. Okay. So we may write L is equal to 2 to the power R, or R is equal to log 2 to the base, log n to the base 2. And what is now R? R becomes the number of bits per sample. Okay? Because each sample after quantization will be represented by R bits. Okay, so this is the number of bits per sample. Bits per sample used in the construction of the binary. So this is pretty much what I have to say about quantization. Then I think we need to discuss the concept of mu law and E law. So before we move to that, if at all you have any doubts or if you have anything to say, you can. If at all you raise up some doubt in the derivation, I will definitely note it down and we'll discuss it in the next class. The reason being that I have to be ready with a concrete answer, because there are few questions in the derivation. If at all there is someone interested to know, he or she can raise that question. Otherwise, anyways, I will definitely tell a few more aspects of the derivation in the next class, which I feel I should. But in the initial go, I do not tell those, because first we need to know what we are doing, and then we have to go back and see that, okay, there was something missing, we need to fill in. That is what we did in the last lecture. We filled in a few missing links of previous lectures. But at least by filling the missing links, maybe we got excited to study the subject more. Anyways, whatever derivations we are doing in this course will help you a lot in maybe in your BPPs, if you are going to do on-campus BPPs, or maybe if you go to some research industry and do something there. So it might be that you will be asked to do something analytical. It might be, although you will be doing a lot in software, but if at all you need to study a system, then you need to be good in analysis. Okay? So if there are no questions, then we will move with the mu law and the A law, which will basically complete our discussion of quantization. So in quantization, the last thing which we should study is the mu law and E law. And after this studying mu law and E law, we will finally study the PCM system. In PCM system, if you have done sampling and quantization, is more or less like a block diagram. Okay? So then we will just draw the block diagram of the PCM system, and we are done with PCM. Okay. So let us study. Let me draw a line like this, because now we are studying quantization in a different aspect. So now, So we will be studying. So we will study quantization. Just hold on. Yes, yes, sorry for the disturbance. So we will study quantization in the context of in the context of PCM or speech. This is important because most of the work in PCM has been done in the context of speech signals. That is what I have already mentioned. That this was basically used mostly in digital telephony. Okay, which means telephone lines which had digital communication as the uh, communication mechanism. Okay, so there PCM was extensively developed by or studied by companies, basically Bell Labs, AT&T Laboratories, and these companies who were making telephones and who were making exchange for telephones, they basically studied this. So we will study PCM in the context of speech signals, and if you have to study PCM in the context of speech signals, obviously first of all you have to study quantization in the context of speech signals. अब नाउ हम लोग नॉन यूनिफॉर्म क्वांटाइजेशन पे जाएंगे कि भाई हम ये देखेंगे स्पीच सिग्नल किस तरीके का है, क्या उसको यूनिफॉर्म क्वांटाइजेशन ही चाहिए या उसको नॉन यूनिफॉर्म क्वांटाइजेशन चाहिए. जैसे कि एक सिंपल मोटिवेटिंग एग्जांपल है कि most of the times any person will speak softly, but let us say there is some situation in which you have to shout, there is some dispute, there is some fight, or you're in anger, so your level increases at that time. Otherwise, let us say if I plot the magnitude values, so most of the time suppose I am speaking softly or like this, suddenly I have to shout in this way, then again I come back in this, then so most of the times your amplitude would be low. Okay, and sometimes it will be high. Another case that there is another person, this is, so let us say for a person A, but there is a person B for whom this person B speaks loudly most of the time, okay, or his normal speech levels are slightly higher than. Let us say this is your normal speech level. Someone speaks softly, someone speaks maybe loudly most of the times, and then when he or she shouts, then his amplitude level is low. Okay, so this is what is we need to put a quantizer for, okay, for such a system, because telephone set can be bought by anyone. Okay, we do not have control on the. We cannot say that, let us say this telephone set is for those who speak loudly, this telephone set is for those who speak softly. Okay, so we cannot have this bifurcation. So we need to make a telephone system for all, for the community, and this is a feature of the community. And people most of the times will speak softly, sometimes they will shout, sometimes they may basically speak out shrill voices as well. Because of somebody is laughing, somebody is doing comedy over the telephone, whatever means. Expressions have different speech amplitudes or properties, and we as users also differ. So now here uniform quantization doesn't help us. We need to have a non-uniform quantizers. So we will design those non-uniform quantizers. Okay. So this is just I have drawn for illustration. They are not. They should not be in notes at least, because they are not the perfect way to draw these things. There are indeed textbooks which give you proper excerpts from papers where these plots are there. Okay. So this is I have drawn to highlight that the inter-user difference, and within a user the difference of the amplitude levels when the emotion is high or it is normal, or maybe it is happy, sad, whatever. So let us draw one property of the speech signal. So one property of speech signal. Speech signal. So it's important to write in the bracket human, because we are not studying speech signals for other organisms. So this is shown below. Okay, this is important to know. Shown below. This will give us a clear picture as an engineer that what should we now do. Let us say if I am plotting the property of the speech signal, you will observe what I am doing. Let me just do it. Suppose this is your level 1. Okay. So this is suppose is 6.4. This is 0.4, 3, 2, 1. Okay. 0.5, 10.6, 0.7, 0.8, 0.9, 0.8, 0.7, 0.6, and 0.5. Okay. And this is, let us say, is 0.5. Okay. 1, 1.5, 2. 1, 1.5, this is 2. And this is, suppose this is 4. 2.53, 3.54. This is not to scale. Just drawn it roughly. So this on the y-axis, what I am plotting is the probability that abscissa means the value on the x-axis. Abscissa value is exceeded. Okay. And what is on the x-axis? So on the x-axis is speech signal magnitudes. Speech signal magnitudes relative to the RMS of such magnitudes. Okay. So let us say we take the speech magnitudes and we divide. Let us say we have taken a big speech sample and we have divided by the every point we have divided by the RMS value of that. So you will find it out. So abscissa is nothing but the point on the x-axis. Okay. So in relevance to x-axis. So y-axis says this will give you the So this says that this is the probability. Let us say 0.4 is the probability that this abscissa exceeds this. So you will see that after 4, this is tending to 0. It means that there is a very low probability that the speech signal magnitudes relative to the RMS value, they are greater than 4. So this graph generally tells us, see, we will write it down more properly, that what does this graph tell us, but in the next class most probably. But today let us just see it. This tells us on the y-axis that this is the probability that the abscissa value is exceeded. So the probability is very high for lower values, or those values which are low. And as soon as you are getting above the RMS values, okay, this one represents that the RMS value and the original value, let us say both are same, then afterwards this is sharply falling. Okay, so it simply implies that most of the time speech signal is of low value. Okay, low value. So if it is most of the time low value, and if you are assuming that the maximum value is 1000 and the minimum value is 1, and if you are using uniform quantization, let me show it. Okay. Suppose let us say we have a message signal which the minimum value is 1 and the maximum value is 1000. So in order to accommodate, what you do is that you are divided into equal values. Just draw it on the y-axis. So your quantization error will increase a lot basically, if at all you are using uniform quantization. So let us say your sample value, this on the y is the sample value, 1 is the minimum, and suppose 1000 is the maximum which Let us say some person who is very loud, and when he or she shouts. So let us say that the amplitude is 1000. Now I am using uniform quantization. Okay, so I am creating a uniform quantization. But the problem is, let us say I know that 70% of the time my speech signal will remain between 1 and 100. Okay, so that let's say this is my speech signal. This is amplitude and this is supposed time. So most of the time it remains like it, and for let us say for very small duration it goes and then it comes back, then again it like this, and then it goes and comes back. It means let us say over this full time duration, most of the time, let us say this it is of low value. But the problem is that if it is the case, we are only using very less number of quantization intervals or very less number of representation levels for this, and this increases our noise a lot. Okay. So what is the solution is that if most of the times the levels are low, we should have more quantization levels here than those for the higher values, because we know that higher values are very limited in time. It means it will be only be present for a very small time. So this is our motivation for studying non-uniform quantization. Okay. So I think we can, at this point, we can stop our lecture for today, and then we can start the new law and pre-law with the background which we have built today in the next lecture, and we will be done with PCM. Okay, in the next lecture, we would think that we would be done at this time. Then we have to do DPC. Okay. So I can say that today's lecture is over. Those who want to leave, they can. Others, if they have any questions, they can stay back.